Notice you have seen this before and this as well. In the last video, we covered these three formulae here. And now we will begin at formula 4. E is equal to mc squared. And then we will continue with the other two in this same video. Formula 4, E is equal to mc squared. We have met this formula before in section A when we were doing mechanics. E is for energy in joules, m is mass in kilograms, c is the speed of light, which is 3 exponent 8 meters per second, or 300 million meters per second. In physics, energy and matter are considered the same entity. So physicists speak and think of mass energy as one thing. So matter can be converted into energy as in nuclear reactors and atomic bombs. And energy can also be converted into matter, but this is much more difficult and not very practical with our current technology. Just to make sure you understand what we are dealing with here in terms of nuclear energy, if you burn fuel, example propane, all you do is break the bonds in the propane molecules and the oxygen molecules, and you form new bonds in their products, which would be carbon dioxide and water. This is an exothermic reaction, so more energy is given off in forming those new bonds than the energy it took to break the bonds in the first place. But no matter is converted into energy. The energy came from bonds being broken and formed. Total mass of the molecules before is the same as that after. So let's consider this molecule here, which is propane. If you combine that with oxygen gas, O2, you will get carbon dioxide, CO2, and water, H2O. If we write that in the chemical format, we will get C3H8 plus O2 gives us CO2 plus H2O plus energy. This equation is not balanced, so let's balance it. Since we have 3 carbon over here, we put the 3 here. We have 8 hydrogen over there, so we put a 4 here. And now that leaves us with the oxygen at this point to balance. 3, 2, 6 and 4, that will give us 10. So we put a 5 in the front here, and now our equation is balanced. Now the mass of the products on the right hand side here, carbon dioxide and water, is the same as the mass of the reactants, which means that all the energy came from, as I said, breaking bonds on the left hand side and forming new bonds on the right hand side. This is not what happens in nuclear reactors. The right hand side on this side here of this arrow, the right hand side has less mass than the left hand side. So some actual matter is converted into energy. So we are talking about two completely different things here. We have looked at this formula before, E is equal to mc squared, and this is a review of what we looked at. How much energy will be obtained if 354 grams of matter were totally converted into energy? Well, we know the mass, and we have to carry it to kilograms. We know the speed of light. We know that E is equal to mc squared. We substitute the numbers we are given, and we get 3.186 exponent 16 joules. Since we only have one significant figure here as the factor with the least significant figure, we are only allowed one significant figure, and so this is our answer. Let's look at another example. How much matter needs to be totally converted into energy in order to obtain 6.4 exponent 14 joules of energy? In this case, we know the energy, we know the speed of light, we want to find the mass. E is equal to mc squared. Make m the subject of the formula, which is equal to E over c squared. Substitute the numbers we have, and we get 7.11 exponent negative 3 kilogram. And we can write that like this if we so desire, which is 0.007 plus or minus 0.0005 kilogram. So we did that equation as a review, that formula. Now we are going to look at formula 5, half-life calculations from word problems. So it's not a formula as such. We have to read the question and reason it out. Now, if you have some radioactive material, it will take a certain amount of time for 1/2 of those atoms to decay. Now, that time is called the half-life of that particular radioactive material. Another way of saying that is that the half-life of a radioactive isotope is the time it takes for its count rate to drop to 1/2 of its original count rate. So if you begin with a count rate of 128 counts per second, it may take 48 hours to drop to 64, which is half of that. But then it will take another 48 hours to drop to 32, which is half of that. And still another 48 hours to drop to 16, which is half of that, and so on. Notice that 48 hours is the half-life, and that is the constant. The concept of half-life is used to calculate the age of once living organic material as well as of certain types of rocks. There are some assumptions that are made. First, that the half-life is constant and not affected by external factors. That's not strictly true, but that is the assumption we will make. 2, the original count rate must be known. Is 128 here? If right now we are at 16, how do we know that the original count rate was 128? That has to be assumed. 3, the current count rate must be known. This is fine. That can be easily determined. And 4, no leaching in or out must be assumed. So no water or chemical brought in or took away some of the radioactive material. So those are the assumptions. Now let's see how this works. So we are going to solve problems involving half-life. Example 1. An old log was unearthed and it was found to have a C14 decay count rate of 4 CPS. That is right now. This is science. We can count on that. Assume that when the tree died, note that, assume, the C14 decay count rate was 128 counts per second. We are to assume that. And we are also to assume that the half-life of C14 is 5,730. If there were no contamination, another assumption, how long ago did the tree die. So we will use those assumptions and find out how long ago this tree died. So first, we will determine how many half-lives elapsed from 128 CPS to 4 CPS as follows. The first half-life, it will drop to 64. That is half of 128. That is one half-life. Then the second half-life, it will drop to 32, which is half of the 64. And the third half-life, it will drop to 16, which is half of 32. The fourth half-life to drop to 8, which is half of 16. And finally, the fifth half-life, it will drop to 4, which is half of 8. Now remember, we are going from 128 to 4. So from 128 to 64, that will be, this will be one half-life. And from 64 to 32 will be another half-life, and so on. So we get 5 half-lives. Now that means that immediately after 5 half-lives, the activity has decreased to 4 CPS. So 5 half-lives at 5,730 years per half-life would give us 28,650 years. So we will assume that the tree died approximately 28,600 years ago, and that is correct to 3 significant figures. Example 2, and this is part of question 6 from CSEC 2014 paper 2. In 20 days, the activity of bismuth decreases to 1/16 of its original activity. Calculate the half-life of bismuth. So first, we will determine how many half-lives there are up to 1/16 as follows. After the first half-life, we will get half of the whole amount. And then the second half-life, we will get half of this half up here, which will give us quarter. After the third half-life, we will get half of quarter, which would give us 1/8. And by the fourth half-life, we have half of the 1/8, which is 1/16. Remember, that is what the question asked us to deal with. That means that after 4 half-lives, the activity decreases to 1/16. So 4 half-lives took 20 days. Therefore, 1 half-life would be 20 days divided by 4 half-lives, and so we get 5 days per half-life. If you find this video useful, please like, share, and subscribe to this channel. It wouldn't cost you anything, and it will mean a lot to me. So we finish with that. Now we come to this last item here, half-life from decay graph or decay curve. Very often, you will be asked to find the half-life of a radioactive material based on experimental data. You will be provided with the count rate at various time intervals. You will then have to plot this data on a graph, and from the graph, find the half-life. In one experiment, for example, the data below was obtained. So you have time in days here and count rate on those days. So at 0 day, when this experiment started, the count rate was taken, and then 10 days later, 20 days later, and so on. At 0 day, the count rate was 100. At 10 days, the count rate was 75, and so on until you reach 80 days, the count rate dropped to 11. Now, you are to use this data to plot a graph, and from the graph, find the first half-life, the second half-life, the third half-life, and then find the mean, which is the average of these 3, to be considered as the half-life of the radioactive source. So this is our data here, and you will be given a blank graph paper like this, let's use this graph paper that we have. You will be instructed to plot count rate in counts per second versus time in days. This first variable always goes on the y-axis, and this other one goes on the x-axis. So first of all, you will draw your two axes. In this case, since all the numbers we have here are positive, we will only be using the first quadrant of our graph paper. So we set up our graph that we have the top right-hand corner available only. So we draw the axes, we draw the x-axis, we draw the y-axis. Then we label them. As I said, the count rate per second, that goes on the y-axis, and the time in days goes on the x-axis. Now that we have that, we have to scale out the axes. Time in days, we are going up to 80 days from 0. So you look at your graph paper and you realize that you could take every 2 centimeters as 10 days. Equal distance on the axis must represent equal amounts. So if 2 centimeters here represent 10 days, then another 2 centimeters here will represent another 10 days and another 10 days and so on. Notice we have 80 here. We can put 90 here. So our x-axis is scaled out. Then of course we have to scale the y-axis, which goes from 100 to 11. So really from 100 down to 0. We do the same thing. We notice that we could have 2 centimeters here to represent a count rate of 10, 20, and so on. Now that we have that, we will plot the points. At 0 days, we have a count rate of 100, and so on. We plot the points, which is about the easiest thing to do on this graph. So we plot all the points. Now comes the most challenging part of this graph. We have to draw a smooth curved line through these points, even if you slightly miss some of the points. Do not connect the points with short straight lines. So we're supposed to get something that looks like this. You may miss a point or two here and there, but connect from up here to down here as far as possible with a smooth curve, even if you miss a few points on both sides a little. Notice you have broken lines here. That is because we don't have data for that, and that is called extrapolation. Up to this point, we have the graph using the given data. Now we still have to use that graph to get the half-life. So I use an online app, put in this data, and this is the graph that I got. Computer tries to get as smooth a graph as possible. Now if we move from 100 to 50, that's half of the count rate. If we come straight across here and then we go down, we will arrive at this point here, which is actually 24 days. We will actually do this with the graph that we just had, but this is just from the computer system. And then we come from 50 to 25, which is half of the count rate. If we come straight across here and then come down to this point, we get 50 days. That's a total of 50 days. So the first half-life is 24 days. The second half-life is 50 minus that 24, which would give us 26 days from here to here. Okay, that was computerized. Let's go back to our graph that we did. To get the first half-life, we will go from 100 to 50. We go across and then come down and we actually get 24 days. That is the first half-life. Then from 50, we come down to 25, which is half of 50, of course. We come across like this to this point, draw a line coming down, and we get the second half-life would be 50 minus 24, which would be 26 days. So the first half-life is from here to there. The second half-life is from 24 to 50. And we do the same thing for the third half-life. So from 25, we go down to 12 and a half, come across here, come down here, and this point here is 73. So from 73, we subtract 50, and we get 23 days. So, in summary, the first half-life was 24 days, the second half-life 26 days, the third half-life 23 days. So if we add all of those and we divide by 3, we will get the average half-life, and that will be used as the half-life of this radioactive source. Half-life is 24 days. Now, is there an easier way to do this? The answer is yes, but it is not recommended by CSEC in this graph, though we were using that when we were dealing with radiometric dating. So the easier way is, you know, this 50 would give you first half-life, 25 second half-life, 12 and a half third half-life. You just come down here, come across, come down, take this final number, where you know you have 3 half-life, which gives you 73 days. Well, if 3 half-lives add up to 73 days, you just divide 73 by 3 to get for 1 half-life, and we get back the 24 days. Now, I'm saying when you are using a graph to get half-life for CSEC, don't use this method. Though this is the method you would be using if you are using radiometric dating to find age. So don't use this way for CSEC using a graph to find half-life. You have to find first half-life, second half-life, third half-life. Then add them up, find the average, which to me is a waste of time, but that's what CXC requires for CSEC. Now, to conclude this section on physics of the atom, we will consider one question taken from an actual CSEC physics paper 2. Now, this is the question, this is the page, the whole question for 15 marks, but it's too small, so you cannot see that. Let me make it a little bigger, and even then it is too small. So I will type over these. So describe an experiment to compare the ranges of beta and gamma emissions in aluminium. So this here that I left out is beta and gamma emissions. Well, that's a description, so we will not deal with that. We are just dealing with calculations. And then it says a liquid fluoride thorium reactor is said to be the new green nuclear reactor. Rewrite the nuclear sequence shown below of how thorium-232 becomes uranium-233, a nuclear fuel, by calculating the numerical values of X, Y, U, V, and Z. So this is too small. Let's make it a little bigger. You have neutron 10 plus thorium 23290 gives you thorium X and Y. Now this is fairly easy. Just make sure all your numbers add up to the same on the top. So 232 plus 1, which means that this here X will be 233. And down here, 0 plus 90 means that this Y here is 90. Now that same thorium, X and Y, 233.90, this is an electron. Electron 0, -1 gives you something here, Pa, whatever that is. Now this is U and this is V. So remember what I said about making sure that each side add up to the same number. So if you have 233 here and you have 0 here, then this one here must be 233 as well. 233, this 0 plus that must give you 233, so this here is 233. Now this is 90, this is -1. What number must you have here for this V so that when you add it to -1 you get 90? And the answer is 91. So 91 plus a -1 would give you 90. Then we come to this part down here. This Pa is that same Pa we had here. So that's 233 and 91. Again, we have that same beta decay here. It's an electron. This is 233. They tell you that is 233. This is 91. So what must this Z here be? We follow the same pattern that we had up here. And so this here must be 92. So when you add 92 to -1, you get 91. So this here must be 92. And you get 5 marks for that, correctly calculating X, Y, U, V, and Z 1 mark each. Now, the next part of the question says that this equation that you see down here shows the fission of uranium-233. And amazingly, they give you U33 with a 92 here. Remember, that is something you had to calculate in the previous part of this question. So it says that the table below provides the data for these nuclides where U is 1.66 exponent -27 kilograms. So you have the uranium atom. This is its mass, atomic mass unit, shortened to U. This SB here, whatever that is, its atomic mass is that, NB, and a neutron, its mass is 1.00867. You are to calculate the energy released in the fission of one atom of uranium. You are also given that the speed of light is 3.0 exponent 8, you can see that quite clearly here, meters per second. So let's make this a little bigger. So you could see the reactants on this side, that's on the left hand side of the equation. You could see the products on this side, that's what you get out from the reaction of those two things on the left. So how do you approach this question? Well, first of all, you would have to find the total mass of the reactants, that's point 1. Then you will find the total mass of the products. Then you will subtract the mass of the products from the mass of the reactants to get the mass of the matter that was converted into energy, but you will get that mass out in atomic mass unit. So you will then have to carry the atomic mass unit to kilograms and then substitute that in the equation E is equal to mc squared. So let's see how that goes. First of all, the mass of the reactants. we have one uranium, which is this, and we have one neutron, which is that. We add them up and we get this mass. That's the mass of the reactants. Now we look at the mass of the products. We have one SB, which is that, which we will add to one NB, which is this, and then we also have three neutrons. We add all of these products on the right hand side and we get this. Notice that the mass of the product is slightly less than the mass of the reactants, as we expect. So let's subtract the mass of the product from the mass of the reactants, and this is the mass of matter that was actually converted into energy, but it is in atomic mass unit. We need to carry that to kilogram, and so we multiply by the factor we are given here, 1.66 exponent negative 27, and we get this as the mass that was converted into energy from one uranium atom. Now that we have this mass in kilograms, we can easily substitute in the equation E is equal to mc squared. This m here stands for the mass that became energy. That is the mass. This is mc squared, which is the speed of light squared, and we get this answer in joules. We are going to keep as many decimal places as possible. Notice we were dealing with 5 decimal places, 5 decimal places, 5 decimal places, 5 decimal places, rather than deal with significant figures in this case. So we actually have 2, 4, 6 decimal places here. That's fine. So this is an actual example of a question that CXC set. And this brings us to the end of this video, Physics 21. It also concludes the required formulae for the CSEC syllabus 2015. But we do have one more video on useful formulae for CSEC, though these are not required by CXC for its CSEC exam. And after that, we have 3 videos on graphs, as required especially by CSEC physics. Graphs are extremely important in physics.